Hi, welcome to the Signal Path. In this episode, I have another product review for you guys, and it's another Rohde Schwarz instrument. There's just so many brand new equipments from Rohde Schwarz, I just can't keep up. So today, we'll be taking a look at the just released FPC1500, the brand new economy entry-level spectrum analyzer with tons of functions and capabilities built into it. It can measure vector measurements on one port. It has a fully independent built-in synthesizer from 5 kilohertz all the way to 3 gigahertz. Excellent performance, lots of different functionality, software built into it. So I'm eager to show you. I actually had this before it was released, so I had a lot of time to play around with it. And there's also a full teardown where I talk about the board and exactly how it's built, both from the RF and the digital point of view. Now these are very long reviews, over an hour, and please let me know if you enjoy these long format reviews. It allows me to get into the detail of how the equipment works and do a lot of different experiments with them. And the point of the experiments is that aside from the people who might be interested in purchasing this, the experiments themselves allow you to learn how to perform some types of measurements. Now all these measurements can become very complicated, and these also serve as tutorials on how to do those type of measurements in the lab. So I hope that it, as a result, is interested to a broad range of audiences. So let me know in the comment section what you think. So let's go ahead, and don't forget to use the underneath the video description there is jumpers, so you can jump to individual experiments if you don't want to watch every little section, but there's lots of interesting information about it, and I'm eager to get started. So let's go. Now, of course, it's not surprising that Rohde Schwarz offers a wide range of spectrum analyzers and some of the best spectrum analyzers in the world. The top-of-the-line FSW models can go all the way to 85 gigahertz, and they're ultra-high performance with quite a lot of functionality built into them for latest and greatest research applications. Now, we have to work our way down all the way until we hit the FPC models, entry-level, economy, affordable spectrum analyzers, and these ones go from 5 kilohertz to 3 gigahertz. Now, even if you purchase a 1 gigahertz model, you can always upgrade it with a key to a 3 gigahertz. So as your applications change and evolve, you can always upgrade this instrument as well. So we're going to take a look at it. I've already updated the firmware with the latest version that's available. The datasheet is also available, which you can take a look at the detailed specification. Some of that we will discuss during the review. So I'm eager to see what we can do with it. So let's take a look at the front panel of the Rohde Schwarz FPC1500. So I'm going to turn it on so we can also see how fast it boots and take a look at the quality of the screen. Now the LCD screen is 10.1 inches. It's a WXGA resolution, 1366 by 768 pixels. It's crisp, it's bright. This discoloration that you see is a Moira effect between the camera sensor and the LCD. Of course, I don't see that. It's a very nice, uniform, clean screen, very bright and crisp. It's not a touch screen, so it has a matte finish, which is fantastic. And touch screens are not that important spectrum analyzers, but again, you won't be missing it on this unit. The only weakness of the screen is probably the viewing angle. From the top and from the bottom, you get some discoloration. Now, most of the time, you'll be looking at it straight on, so you're really not going to have much of a problem. Horizontal viewing angle is not a problem at all. On the RF input ports, you have a generator output at the bottom left here, and then you have an RF input. Now, both of them are 50 ohms, 50 volt DC. AC coupled. They can take up to 30 dBm, which is fantastic. Very good to have high levels of protection. The general output is also connected to the internal synthesizer. There's a built-in bridge, so you can do vector response measurements. It has a very powerful independent built-in synthesizer, which is fantastic. We will take a look at that. Number pads can be used to enter letters as well. Nice different color range buttons. This is always handy to have. And this rotary knob is good. It's got good indent. Pressing. There's audio feedback for buttons. You can turn that off. Soft buttons here depending on the context on the screen. Every button up here is necessary. I use all of them all the time. Good choices. This screenshot button, I would have probably liked to have a source button, because again, it has such a good source inside. You want to have quick access to it. You have to access it under the measure menu. We will see that. But this is useful in a university lab environment. If you want to capture a quick screenshot, this is the way to do it. It saves it on the USB disk. So it works really well. You also have 2 USB ports and a headphone jack in the front. Overall, very nice, clean look. It's got the indents here, so you can actually put this on its face and it won't hit the screen, the knob, or the RF inputs. I wish every instrument had that. It makes it really easy to move around and look at the back or even disassemble it. And we will see that when we take it apart and what's going on the inside. Now, one of the cool things about the GUI, about Rohde Schwarz in general, is that they have a really nice signal flow graph. And we've seen this in all of their instruments. And this is such a good idea that even Keysight has been adopting it in their recent spectrum analyzers. Now, Rohde Schwarz does it in all of their instruments, where they show you exactly what is happening to the signal, what components is going through, what kind of computation is being done on it, what setting the instrument has. And this is super handy, and you can go from setting to setting, and if you just click on it, you can change everything that's associated with that particular setup. And this is a good, easy way to get an overview of what's going on in the instrument. Other settings like instrument setup allows you to turn on the Wi-Fi, which is built in, and configure it and connect to a LAN and so on. And we will take a look at that as well. In the user preferences, you can set what kind of a file saving time, dates, captured in data sets, and so on. Very typical stuff. Now for this particular one, we are looking at, and it's interesting, the controller version doesn't show up very well. Sometimes it shows up, sometimes it doesn't. It started happening after I updated to version 1.3. Doesn't seem to have any negative impact on anything. But this particular unit is fully loaded, so all the options are there, up to 3 gigahertz, preamp is there, Wi-Fi support, demodulation, and so on. We will take a look at all of these features, and they're all quite nice, packed with lots of interesting functionality. And here's the back of the unit. Of course, we have external trigger in as well as the reference in, so it's a switchable, so you cannot have an external reference and trigger at the same time because you're using the same connector. LAN, USB, of course, the regular power connector, fuse, and the power switch, a hard power switch. And you can see I've already voided the warranty on this one because I've taken it apart for recording the internals. So let's take a look and see what we have inside the unit. Now, as you would expect, it is almost completely hollow. It has so much free space inside it, and there's some things you can do with that free space, as I will tell you in a second. So here in the back, we have the power outlet coming in, as well as the power supply. The power supply is a 12-volt power supply made in China, even though the unit itself is actually made in Czech Republic. It is designed, of course, by Rohde Schwarz. I'm not sure about the power supply, maybe an off-the-shelf component. But here's the power going in, nice earth connection, nothing unusual there. I'm a little bit surprised that the power supply doesn't have its own shield. Of course, it has to be very well shielded from the RF input, and I'm assuming that it is, and we will see it in our test. But it's a little bit unusual not to have a shield there. Now, we have a single 12-volt output from the power supply directly onto the motherboard, which means this is a perfect candidate for a battery-operated unit. So you can easily modify this and put a battery in it, given that there's so much free space here, connect it and having an extra connector somewhere in the back to charge the battery, or even retrofit it to be automatically charged from the a line coming out and having clever switching over between the power supply and the battery. So it's fantastic for that. I think it would be a nice little project. This is the back of the keyboard. You can see the signal going directly to that. The LCD is on the back there, and it has a separate ribbon cable for it. So let's go ahead and turn this and see what we get on the other side. And you would expect exactly this. We have a main PCB, which has all of our components, including the application processor and everything else on it. The USB ports here in the front are directly connected to this board as well, and our RF deck over here, which we will take a look at in detail. Some processor in there. We have to take a look at what that is. LCD connection, keyboard connection, USB, Ethernet, and if you look, sneak in there right now, we have our Wi-Fi module right there. So let's go ahead and take this one step further and take a closer look at that PCB and see what we can find on it. So let's take a detailed look at the main motherboard inside the unit, and that this single board contains everything, the digital side, analog, and the RF side all on one board. Now I've left the RF shield here on top just to show you that they have also extended the RF shield to cover the main application processor and using it as a heatsink, as well as of course covering the RF deck. This is a clever use, of course, and is they're not the only people who've done this before, but because this is a low power instrument, allows this structure to be completely fanless. So let's go ahead and remove that so we can see what's underneath it. And it is stuck to the board using some thermal putty to take the heat away from the main digital processor. Now, the main processor here is a Xilinx Zinc SoC. The Zinc SoC family is quite a wide, extensive family of FPGA with our ARM core processors and peripheral controls built into it. It's very common to find them in this type of instruments. And this particular one is a mid-range, about $125, $130 a unit, which has a built-in ARM core processor up to 1 gigahertz, peripherals to control memory as well as other interfaces. So quite a powerful SoC, and it's no surprise to find them in this class of instruments. Now, moving from the right side here, we have clearly our Wi-Fi module, and it is capable of having an external antenna, but you're using the internal antenna, so the RF field is confined to this region of the board, and you can see the RF input is all the way here. So the RF input and the Wi-Fi are as far as possible on this board, and that makes sense because you want to eliminate any coupling at all. There's an Atma processor here, most likely to interface with the RF, the Wi-Fi module over there. Nothing surprising really. There is an interface here which is not being used, a battery, USB ports at the top if you've seen before, USB controller chipset, gigabit Ethernet controller chipset. Here's an audio DAC with built-in Class D amplifier. This is obviously used with the headphone jack as well as the built-in speaker to be able to drive and produce audio signals in the demodulation capability that this instrument has. A very clear separation between the analog ground and digital ground on this board. So therefore, this DC-DC converters that you see up here, filtering, inductors, capacitors, or whatever they're doing here to clean up the supply, are for the RF DAC. So they have separated this so that you can clearly see that all this extra filtering is done to provide a very clean and quiet supply for the RF portion of the instrument. So that kind of takes care of this side. Some status LEDs, nothing unusual. On the other side, from the digital side, really there is nothing that we haven't seen before. There is a LCD controller connection there, which is being driven directly, of course, from the FPGA. You can see the BGA footprint package at the back. Keyboard controller. Here are the voltage regulators as well as some potential DC-DC converters. You have to look closer to see if they've done any actual DC-DC converters. The inductors and the capacitors may simply be just for very high level of filtering. Now going back again on this side, we can now take a close and look and see how the RF portion of it is behaving, because there's quite a few components on that. Now the RF portion of the circuit has multiple connectors. We have a connector over here, which is the main RF input of the instrument, and we have a connector here, which is the RF output, as well as the RF input for the reflection measurement. So let's go ahead and follow the RF input. Now this has all the components you would expect to find at the input of a spectrum analyzer. We have AC coupling, preamplifier section, low pass, filtering, a programmable digital selectable attenuation section. In this case, we have a switch attenuator in the front, a digital programmable attenuator which then follows it. Now the signal after that would have to go into frequency conversion. Now, like pretty much any spectrum analyzer, we have multiple IF conversion. The first one is an up converter, which converts the signal beyond 3 GHz, and this is the IF input, and this is the RF output, and this is the LO into this mixer right here. Now the RF output, which now sits above 3 GHz, will have to go through a filter, and I think this is a SAW filter, although I could not find any information about it. So the LO generation is quite complex and interesting as well, and we'll go over that. Now after the first IF conversion, it's not very clear to me where the second IF conversion actually takes place. It could be in this component, and the reason I say is because this is the IF conversion which follows the second one. It's the third IF converter, and this is a 900 MHz down converter. So something in between these two must be bringing the frequency down within the operation of this mixer over here. After that, we have our IF signal, which is differentially filtered very cleanly. You can see over here before going to our A to D converter. This is a TI 125 megasample per second A to D converter, and you can see the proximity of the data converter to the zinc FPGA, and this makes sense because you want to have as minimal digital routing after the conversion has happened before you hit your FPGA. So they put that right at the edge of the RF to digital portion, which is nice and of course expected to be designed this way. So going back over the filtering again, we can see some components over here, and this path is an LO path, and the LO system is really complex. So we have two components down here. These are both Rohde Schwarz labeled components, and they work together, and they make up the main core synthesizer of the entire instrument. So all the super heterodyne IF conversion stages, all of the LOs that go into multiple components, these are all tied and driven by this main synthesizer, except for the RF generation for the output, and I'll talk about that at the end. So these two components, I don't have any data sheet for them because they're designed or at least labeled by Rohde Schwarz, and they tend to do this because they're looking for a particular set of frequencies, some hopping frequency speed, some sweeping speed, as well as phase noise requirements, which they want to meet because that determines the performance of the entire instrument, and it is done this way. So we have a portion over here which has multiple sections, which is much more clear on the other side, to get a very clean LO generation, multiple filtering sections. We've seen this architecture particularly in synthesizers. So now, having said that, we can actually flip to the other side just momentarily. So we can see the other side. Take a look at some of the LO distribution. So here's the back of those two components that Rohde Schwarz has designed, and you can clearly see there is multiple sections, multiple filter section with selectable switches at the output, and the signal then comes over here. And this is the LO going to the very first mixer that I showed you, and it coupled to this side and is being fed back. At least this is what I think, and this is the way they close the synthesizer. And then at the same time, they send a signal over here, and this goes through the board to the other side and is the frequency reference LO for the 900 megahertz down conversion stage. At the same time, this portion uses an LO signal again generated by the same circuitry in order to create the clock for the final A to D converter. You can see a differential line going right over here, going through the board to the other side. So the differential clock of the A to D converter is also generated ultimately by the same synthesizer core architecture. All of these are locked together as they have to be in order to create a predictable IF signal planning, which is critical in spectrum analyzers. That's where all your harmonics and all your images land. This is why it is so important to do proper filtering on the LO and on the RF to make sure that none of the images land on top of each other. Otherwise, your spectrum will be full of spurious tones. So having said that, you're going to go back on the other side again. And now it becomes a little bit more clear on how the full RF signal flow is. So RF going through here, conversion potentially here, conversion here, A to D converter, synthesizer portion here, synthesizer portion here, and on the other side, and the frequency for the data converter is also generated on the other side. So now let's take a look at the RF output. So the RF output, in order for it to work like a network analyzer, a one-port network analyzer, is going to have multiple down conversion paths in order to be able to have a reference and reflected wave section. So here's these two components. This is a Hittite or analog devices, VCO, PLL, and it's a synthesizer. So these guys work together, followed by some digital attenuation. There's some Rohde Schwarz part number again here. I'm not sure exactly what it does, but probably to drive this bridge that they have built. So the signal goes out, goes back in, as well as going out and coupling this way. So it's multiple paths. We have two identical down convert mixers. So we have the signal, forward signal, reflected signal, down converted again, going through these filtering stages, going into a two-channel A to D converter. So you can see how by using the digital data coming from this A to D converter and proper calibration, you can do reflection measurement, a vector-based reflection measurement. Again, the A to D converter is very close to the FPGA. Now, on the other side, you're going to have another synthesizer because you have a synthesizer that generates TRF, and you also need a synthesizer for the down converters. And we can go back here, and we can see that exactly the same thing. Here's another synthesizer identical to the first one, designed here to drive the LOs of the mixers. Very cleanly and nicely done, put together. So this is as simple as it's going to get. And when I say simple, of course, I mean using the minimum components required in order to get very good performance, and this is a Rohde Schwarz design, and I'd expect nothing less than that. So this is how we can do a S11 measurement. In vector based, we can do a scalar S21 measurement going from here all the way to here, and of course we can do spectral measurement. Now, because we have some IF bandwidth with a particular bandwidth coming out of here, we can do some digital demodulation as well. The A to D converter will be able to take care of that in the DSP domain into the Zinc FPGA. So all of that really comes together quite nicely. I don't think there is anything unusual except for this somewhere in between this IF conversion, perhaps. If something you guys know about it, you can let me know in the comment section. But overall, the architecture, I think, makes sense. There's no mystery there. Now, the other thing I wanted to point out, throughout this entire board, there are tons of UFL connectors. So you can see UFL connectors everywhere. So you can plug in a cable in there and look at the signal along the entire path and see what is the harmonic, what is the frequency content, and you look at exactly what happens every step of the way. This itself is really interesting, and it might be worthwhile just to have a video just on that. And in fact, this would make a really nice evaluation board for education purposes, because the students can then plug into there and see what's going on in a modern kind of state-of-the-art economy type of spectrum analyzer, plus RF generator and reflection measurement, vector measurement. All of that stuff is there. You can see even the input of the A to D converters in the differential domain can be measured directly. This is fantastic. I wonder if this is something that they have in mind or are planning to actually release. Again, at the back you can see UFL connectors all over the place for looking at the synthesizer outputs, for example, here. So for our experiment, I want to characterize this amplifier. Now, the part number for this unit has been rubbed off, so I'm not exactly sure what kind of an amplifier it is. I do have a few information about it. We know that it runs from a 15-volt power supply with these two pins, and it does have a gain control pin as well. Now, it says AGC, automatic gain control on it, but that's in a closed loop system. It's really more of a variable gain control amplifier. So we can go ahead and see if we can characterize that particular aspect of it as well. It has an input and an output, and if you take a look inside, it is hand assembled using several mimics. Now I want to know to what extent I can characterize this using just the FPC1500, whether I need additional equipment to fully find the specifications of this unit and what limitations there are with the spectrum analyzer when it comes to doing something like this. So let's go ahead, hook it up to the unit and see what we can do with it. So to start things off, we're not going to use the internal generator of the instrument. We're going to use an external generator, which is sitting right behind this unit right now. This is the Azure and EXG vector signal generator. So the output of that is connected to the input of our amplifier, and the output of the amplifier directly goes to the main RF input of this unit. So let's go ahead and take a look at the screen. I want to run through a few experiments using a clean external source, and then we'll look at the internal source for some of the remaining tests that I would like to do, and we'll get a good idea of both the performance and the limitations of these sources. So first thing first, let's apply power to our amplifier, and here's our power, and of course right away we can see a change in the noise floor, and we get a rough idea of the bandwidth of the amplifier without doing anything. And the reason for that is this is a fairly high gain amplifier and a high noise figure amplifier, so we have a lot of noise at the output of the system without any input, and we get a rough idea of what we're dealing with in terms of the bandwidth of the system. Well, having said that, let's go ahead and apply some signal to it. So right now let's start testing this at around a frequency of, let's say, 1.2 gigahertz. Now we can see that this definitely, if this is 3 gigahertz in the middle, we have 1.5 gigahertz, so we definitely have bandwidth in the 1.2 gigahertz region, so we can go ahead and apply some signal to it. Now to be on the safe side, since we don't know how much power this is going to generate, let's go ahead and apply a minus 50 dBm tone at the input of the amplifier. So we're going to set that up right here, and I'm going to enable that. And there it is. We can see indeed a tone coming out. So now the input signal is at minus 50 dBm. We're going to go ahead and press the marker button here, and it's going to do automatically a peak search for us. So the frequency 1.2, almost 1.2 gigahertz, minus 23.9 dBm. So now let's say minus 24 dBm. Now we're putting in minus 50, we got minus 24, we have about 25, 26 dB of gain, which is exactly correct. That's how much gain this amplifier should have. So indeed it is working. Now let's try an overload condition. Now this instrument is supposed to warn us if there's an overload condition, and it's supposed to tell us that the IF system is being overloaded. So let's go ahead and increase the amplitude. So I'm going to continue increasing it until this signal is above minus 20 dBm. Remember, the reference is at minus 20 dBm. So I can keep going, and I don't get a overload condition, and I can keep going and really compress the system. And now we're getting some spurious tone appearing, and this spurious tone over here is not from the system, is actually from the instrument itself, because the IF is being overloaded. Now for some reason it doesn't tell you an IF overload condition on a full scale sweep. However, if I go ahead and change this, and I change my start frequency to, let's say, 1 gigahertz, and then as soon as I do that, you can see we're getting an IF overload condition. So it is not able to tell that we are compressing it in a full scale. Now we get a warning and a noise, which I'm sure you can hear. So I'm going to go ahead and bring the power back down to clear the overload condition, and as soon as we clear it, of course, it's fine. Now we are 6 dB above the reference, and it's perfectly fine, so it has some margin built into it. So let's go back to minus 50 dBm. At minus 50 dBm, we're back to where we were. So it does work, it just doesn't do a very good job when it is in full frequency scale. So let's go ahead and preset that one more time, and let's go ahead and change our amplitude reference. So instead of minus 20 dBm, let's go up much higher, and let's go to a 30 dBm reference. Now at the 30 dBm reference, of course, we have a significant attenuation added. Here we go, we have an attenuation of 40 dB on the front end of the unit, so it's well protected, and it is supposed to survive up to 30 dBm, so we should be able to try and compress the amplifier now. So let's go ahead. Here's minus 40, here's minus 30 input, minus 20 input. Let's enable the marker one more time. So we're looking at the 6 dBm output. Now we're looking at the 14 dBm output, and at a 15 dBm output. So it doesn't look like that the output signal is growing any more than that. So the compression is around 15 dBm. That also is correct. That's exactly what it's supposed to be. So let's go back to minus 30 dB input, and the signal then goes back to minus 3.9 dBm. We can go ahead and change the reference back to a higher value so we can get a better noise measurement. Now, one of the nice things I like about the system is that if you go over here and you go onto a auto range, it will auto range the reference so that it will place your signal in the best viewable position. I don't really normally like auto range features in spectrum analyzers. I like to know exactly what everything is set to, but indeed it is a useful thing, especially if you want to quickly get an idea. Now under the attenuator menu, it does have a low distortion and a low noise setting. So right now it's in automatic low distortion, meaning that the instrument would adjust the attenuation as required to give you the best distortion parameters, but you could also change it to get the lowest noise parameters. Now let me turn off this input for a second and go back. And we also have the option of turning on the preamplifier. Now if you turn the preamplifier on, you get an attenuation of 40 dB. Of course, we're protecting the internal of the circuit. You can change that attenuation, and this will give you an additional noise figure improvement of the instrument itself, so you can get a better displayed average noise level. And let's take a look at the impact of the preamplifier. So here I have set the reference to minus 30 dBm and the attenuation to 0 dB. Now as you can clearly see, we still see the shape of our amplifier's noise. Now if I enable the preamplifier, we can see that of course the low frequency portion has no impact. That's because we are dominated by the noise of the amplifier itself and not by the noise of the instrument. But we do get some benefit at the higher frequencies, and that's because the low pass filter behavior of the amplifier itself pushes the noise very low at the higher frequencies, which is beyond the operating bandwidth of the amplifier. And then when you enable the preamplifier, you get the noise floor benefit from the instrument itself. So I'm going to turn it on and off one more time. You can turn it off, and you can see we indeed have an advantage over here. So if you have a signal buried in here, you can actually discover it by using the preamplifier. So this is exactly what I've done. I have a signal going into the amplifier at 2.9 gigahertz at minus 76 dBm, which is above and beyond the frequency of operation of the amplifier, and I've enabled the output, and you can see without the preamplifier you don't see anything. But if I turn the preamplifier on, because of the advantage we get in the low noise floor here, you can see that there is indeed a tone peaking out there. So the preamplifier is a great option to have on any very low noise floor measurements you want to do. In this case, because the amplifier has so much excess noise, you won't see it anyway, but you can see that it will give us advantage at higher frequencies, which is great. So now let's investigate the linearity of this amplifier. Now keep in mind that this is not necessarily the order in which you would characterize an amplifier. You would look at its frequency response, power consumption, and other parameters before you get to this point. The reason I'm going to look at it first is because it helps us explore the features of the FPC1500 in a reasonable way, and eventually we will get to measuring other parameters too. So just keep in mind when we're doing this experiment. So I want to measure the linearity. So what does that mean? Well, I want to look at the third order intercept point, look at the inter-modulation products and compression and so on, and see how it behaves across different frequencies. For us, let's look at it at 1 gigahertz. It's a nice easy place to do that. Let's go and change the amplitude. Since we're going to be pushing the amplifier at higher output powers, let's make sure that we are sitting at a good attenuation and a good reference level. There it is. This is a full band. I'm going to enable the input. There's the input to the system, and it is a 1 gigahertz input, and you can see the second harmonic coming out. Now we don't know if this second harmonic is from the amplifier or it is from the fact that the synthesizer itself is generating a second order harmonic. So for that we'll have to change our setup in order to do that measurement, and we will do that after this one. So for now we're going to look at the 1 gigahertz tone so we can look at intermodulation products. So let's change the center frequency and put the center frequency at 1 gigahertz. Let's change the span of the instrument and look at a 30 megahertz span so that we can see the signal quite nicely. And I'm going to change the bandwidth a little bit so I can show you an interesting effect here. There it is. So right now we're looking at the resolution bandwidth of 100 kilohertz sitting at 1 gigahertz, and if you look carefully you can see an asymmetry in the upper and lower side phase noise around the carrier. So why is that? Well, I think it has to do with the frequency planning of the FPC1500. It may be that around this frequency, whatever the internal LO frequency is, it might be switching a multiplication factor, and the internal phase noise of the instrument is actually changing between just below 1 gigahertz and just above 1 gigahertz. So up here you're seeing higher phase noise, and here you're seeing lower phase noise. Now this phase noise is not dominated by my synthesizer, is dominated by the FPC1500. The synthesizer has a much lower phase noise performance. Now I can show you that if I change the center frequency just above 1 gigahertz, you can see that we have now a balanced phase noise on both sides. And if I go just below, we have balanced again, except that it is lower. So it's clearly something to do with the frequency of the FPC1500 itself. Now if I change the bandwidth once again to, let's say, 30 kilohertz, that problem completely goes away. So it's not really an issue, it's just something to keep in mind. If you happen to see a asymmetric skirt, you can know that it might be from the FPC1500's internal synthesizer settings. Okay, great. So there it is, there's our tone, and we can place a marker on the tone, of course, and we see it's a 6.4 dBm tone coming out of 1 GHz. So I'm pushing the amplifier reasonably hard there. And by the way, erasing the markers is pretty straightforward also. There you go, you can erase it quite simply. Now, this is not going to give us third order modulation products, of course. We need to put 2 tones into it. And my synthesizer is able to produce 2 tones. So let's enable that. And there it is. And as soon as I enable that, we can see the 2 tones being generated around the 1 GHz carrier. Now, the Keysight EXG is a very good synthesizer, so it has very little LO feed through there, and its intermodulation product is really good. It's far better than the amplifier, and so in fact it's generating only minus 20 dBm total power, so it has no problem generating very clean intermodulation products. So here we see our 2 tones. Above and below 1 GHz, they're 2 MHz apart, and here's our third order intermodulation products, and even higher order intermodulation products can be seen peeking through the noise floor. Now, normally when you want to measure the TOI, you can put markers on these tones and do the necessary subtraction, division, and so on, and calculate the TOI and calculate the intermodulation products. But the instrument has built-in measurement capabilities, and quite a few of them actually. So we can go under measure, and we can go under measurement mode, and here we have a whole bunch of measurement capabilities: channel power, third order intermodulation, spectrogram playback, as well as that's not what I wanted to do, as well as harmonic distortion, AM modulation depth, and occupied bandwidth. So it has quite a few measurement capabilities. Let's go to third order intermod products. There it is. And as soon as you do this, it will automatically place the markers at the correct locations, and it will catch the right terms and the intermodulation terms, and it will give you a TOI. There's our TOI, 23.4 dBm. Very easily calculated. Now, one thing I wish it did is that if it also gave you the IM3 products in dBc, that's a useful parameter, especially if you're doing modulation calculations and you want to know what the impact is on your modulation and on your EVM error. That would be a useful thing to have. Now, we can, of course, just subtract these 2 numbers, 35 minus 3.6, about 32 dBc IM3 terms. That's not bad, and corresponds, of course, to a TOI of 23.4 dBm. And that number is correct. That's exactly what this amplifier should do at an output of just around 6.5 dBm. So now I can do some experiments. I can reduce the input power and increase the input power to the amplifier and see how it affects the TOI. So let's first increase it. Now, increasing it would mean that we're pushing the amplifier closer to the compression, so we expect the TOI to begin to suffer. So let's go and try this. I'm going to increase it, and indeed, as you can see, the TOI is dropping. The output power is now 7.2 dBm, so we had a major degradation in the TOI of more than 3 dB or so by just going off about 1 dB of power, which is consistent. So that means that you don't want to operate the amplifier at such a point, because your TOI is going to get worse and worse. Now we can back off on the other direction. So this is where we started. TOI was 23.4, and I can go back down a little bit. And when I go down, we get a little bit of an improvement. You can see we're hitting about 24, but then at some point then there is no more improvement, because we just have a basic relationship between the intermodulation products, main tone, and it's going to have a constant TOI. So if I keep going, eventually we'll reach a point where the harmonics intermodulation products are now below the noise of the instrument, and we can no longer see them. So in these situations, what you can do if you really want to measure it even lower is to reduce and to increase to reduce the resolution bandwidth, so that you can get a little bit lower noise, displayed noise there. So if I go to, let's say, 3 kilohertz, I will begin to see the intermodulation products peak from the noise again. But unfortunately, for some reason, the instrument can't catch those tones anymore. So if I go under measure, and if I press search signals, it will search for them. It will find the main 2 tones, but it won't find the intermodulation products, even though they are there. So it's giving us an erroneous TOI. So in fact, if I increase the power back to where it was, all the way up here, so this is where we started, and I do a search signal again, for some reason, it doesn't know that the third order intermodulation products are all the way up here. It thinks they're all the way down there. So it's saying the TOI is 42.7 dBm, which is insane. Of course, there's no way an amplifier like that will be able to do this. So unfortunately, it can't catch it. It has to do with the resolution bandwidth. This must be a computational mathematical issue, not being able to find those tones. And this can be easily fixed in firmware that I'm sure they will do. So if I go ahead and change the resolution bandwidth to higher, 10 kilohertz, and it still doesn't know where they are, but as soon as I hit 30 kilohertz, then it finds them again. So it's just a minor issue. Hopefully they will fix it. Just keep that in mind if you're using this feature. So now that we know the TOI, let's take a look and see what happens to the harmonics. Now, we've been using an external synthesizer because I want to be able to generate two tones, but we can also use the internal synthesizer. One of the greatest features of this instrument, it has an independent internal synthesizer which you can use at any frequency you want, regardless of what frequency you're using the spectrum analyzer at. This is huge. I can't remember seeing another instrument that provides this at this level, at this kind of a level this class, this instrument is sitting at. So I'm really excited to try it out. Let's see what happens. So let's take a look at the internal generator, which is really capable. And what I've done is I've connected the output of the generator directly to the input of the RF input. So I'm measuring the internal source using the spectrum analyzer itself. So let's go ahead and enable that and see what happens. Now, the source control is under the measure menu, and the reason for that is because normally when you're using the generator, you're trying to measure something, so I guess it's placed under the measure submenu. It'd be nice to replace this button with the source button because it's so capable and there's so much you can do with it. So let's go under the source here, and we can go ahead and enable several different modes of operation for the internal source. So we have a CW, a coupled CW, and a tracking generator, which is fantastic. This just gives you so much flexibility. So let's go ahead and enable the CW, and you can see that as soon as you do that, we have a CW right now at 1.5 gigahertz. The power here is minus 20 dBm, and you can set this frequency anywhere in this band independent of the sweep of the spectrum analyzer itself, which is fantastic. So let's go ahead and change the amplitude here. Let's go to 0 dBm so we can see the dynamic range of the internal source. Going back to measure here and back to source here. There it is. So we can put a marker, and we see that indeed we are generating 1.5 gigahertz at minus 20 dBm, which is exactly what we would expect to see from the source. Now I can go ahead and change the amplitude and see what kind of range I can get from the amplitude here. I can change it under level here. So I can go all the way down to minus 30, which is great. It's a little bit more than minus 30, so this is not completely accurate at the lowest range here. So minus 30 dBm is the lowest value, which is good because if you have an active amplifier, you want to make sure that you have a low enough signal not to saturate your amplifier. Otherwise, you're going to need internal or external attenuators. So having said that, let's see what is the maximum we can do. So we can go all the way to 0 dBm. That's the highest value. It's just a little bit under 0 dBm. And that's very good. 0 dBm is also high enough for you to be able to measure fairly lossy material, fairly lossy components, and still have dynamic range to fit within the spectrum analyzer and be able to make a very low signal level measurements. So that's excellent. Now, the dynamic range of the generator obviously is because of the internal synthesizer and because of the variable attenuator that we have. This is a purely an electronic attenuation range there. So it all works very nicely. Let's go and change the frequency. Let me just turn the marker off for a second. So we don't need it. All markers off. And let's go back under the measure and source, and under the CW menu, let's enter a different number. Let's say 100 megahertz. There it is. Now, as soon as you enter 100 megahertz, well, you see all the harmonics. So indeed, the internal source isn't completely filtered very well, and it does have a lot of harmonics. As you go into higher frequencies, obviously, I can change the frequency, let's say, to 500 megahertz, and you will see that you will still have, of course, all the harmonics. And depending on the frequency, you're going to have a different ratio between the fundamental, second harmonic, third harmonic, and so on. At low frequencies, the second harmonic is almost non-existent. We can see in the second harmonic right there is very, very low. So let's go and measure the total harmonic distortion of the source using the instrument itself. Now, it has a built-in measurement capability, as we saw earlier, and we can go ahead and measure harmonic distortion directly. Now, when you enable that the very first time, it doesn't have enough harmonics, so it's only trying to measure up to the second harmonic, and it can't really find the second harmonic, so it's telling us that THD is only 0.2%, which is of course not true. So we can change the harmonics. I believe I can go as high as 6. So let's enter 6. Now it's going to look for 6 different harmonics, and I have to say adjust setting. And there it is. You can see it found the fundamental, second, third, fourth, fifth, and so on. All the harmonics are being found, the markers on all of them, values all reported quite nicely, starting from 100 megahertz, and we have a THD of about 35%, which is just under 10 dB. So minus 10 dB obviously is not very good, but for narrowband measurements, it really is not an issue. Given that it's a fully independent source, it's really quite good. If you want to use this internal source to do THD measurements, you would need an external some kind of a cavity filter so they can filter all the other harmonics. I've done this experiment before. I won't repeat it here again, just in the interest of time. But nonetheless, you can see that it works quite nicely, and you're going to have a fully capable internal synthesizer. Now, perhaps even more exciting capability of the synthesizer comes to the fact that it can do tracking generator as well as offset tracking generator. Those are really, really useful. So let's go under measurement, under source. Now, the coupled CW is also useful, and all it does is that it will couple the frequency coming out of the built-in synthesizer to be at the center frequency of whatever it is that you're displaying on the screen. So right now our center frequency is 349 megahertz, therefore the frequency coming out of the internal synthesizer is also 349 megahertz. So if I go frequency, let's say I set the start frequency to 1 gigahertz, and I set the stop frequency to 2 gigahertz, our center frequency in this case would be 1.5 gigahertz, and that's exactly where the synthesizer frequency will land on. So it kind of follows you, it follows the middle of the screen. This is really useful when you want to see any additional harmonics or tones that are present near the LO, especially for frequency conversion measurements. So this gives you a tool to measure nonlinear circuits now in frequency conversion mode, which is fantastic. Again, because it has a fully independent synthesizer, and that is further obvious when you go into the tracking generator mode. And now in the tracking generator mode, it also gives you a tracking generator offset, which is great. It means that instead of the LO frequency following the center frequency of what you're seeing, you can give it an offset, so it follows with a gap in frequency between the carrier and what's being shown here. It means you can look at now conversion gain in mixers. If you have a third source outside to drive your LO, let's say, you can find IF bandwidth, RF bandwidth of mixers in frequency conversion mode, which is great. Again, these are fantastic features on what is considered really an entry-level instrument. So it becomes kind of a one-tool, do-it-all situation. So I can say, for example, track everything with a tracking offset of 100 megahertz, for example. There it is. So now it's going to look at a 100 megahertz offset, and obviously at a 100 megahertz offset, when you have a through between the tracking generator output and the input, there is nothing. So you see nothing. And if I change the tracking generator offset to 0, which is 0 hertz, now you're going to have the frequency response all the way at the top of the screen, which you cannot see very well because it's kind of maxed out over there. So I think it's great. So let me change the amplitude level here. Let's put it to 10 dBm. So you can see the line there. There it is. There is our tracking generator following the cable, of course. Now this is not normalized, so naturally there's going to be some minor variation, but we can normalize this and then use it to measure the frequency response of our amplifier, which is exactly what I want to do next. And let me set that up to show you how we can do that. So let's go ahead and set this up. Now we have to be careful here when we set it because we're measuring a fairly high power amplifier. So let's go under measurement and go under source and set the tracking generator. And we want to set the tracking generator to go in the full scale, which is what is done right now. So now, because this amplifier has about 20 to 25 dB of gain, if I put minus 20 dBm into it, which is what the tracking generator is set to right now, it will generate about 5 dBm of output power. Now 5 dBm is where I measure TOI, where I'm interested in operating the amplifier, so I'm going to measure its response at that power level. Normally you want to measure as small signal as possible, but I'm interested in somewhat high output power frequency response. So this is why I'm doing it at minus 20 here. Now the reference here is also set to minus 20 and the attenuation 0, which is not good because it means that when the amplifier generates 5 dBm, you're going to saturate the instrument and you're going to end up measuring the instrument and not the amplifier. So we have to make sure we take care of that as well. So we're going to set the amplifier amplitude here. We're going to go to a reference of 10 dB, which is an attenuation of 30 dBm, and that's going to be fine for measuring the output power we want to. Now the disadvantage of doing this is that now we can no longer measure the isolation of the amplifier very easily because we have so much attenuation. The noise of the instrument is going to dominate, and we're not going to be able to see the isolation response because the isolation of this amplifier when it's powered off is very high. With the addition of 30 dB of attenuation from the instrument, will be in the noise floor, even for very small values of the resolution bandwidth. But nonetheless, I'm going to make the resolution bandwidth at 300 kilohertz. So now that we are setting the instrument in every setting that we want to, we can go ahead and normalize. If you normalize and then change these parameters, you're going to lose your normalization. So you can see here we have the uncal written because it's an uncalibrated S21 measurement. This is a scalar measurement, keep that in mind. So let's go ahead, try that, and we can go normalize. And it's going to ask us, of course, for a through, which I've already connected, so we can say continue. There it is, it's going to do that for us, and there it is nicely at 0 dB, so it's all calibrated for us to measure. Now I can also go under the amplitude, and I can change the reference position, and I can move the reference up a little bit so that we can see the gain of the amplifier easily. Now remember, everything is normalized. We're not going to touch any of the settings anymore. Now that it is set up, I can go ahead and put the amplifier and remove the through, and then we can power the amplifier on and look at the response. Okay, so here's the amplifier when it's turned off, and of course we see nothing going through, and I'm going to turn the amplifier on, and here's the amplifier powered on. And we see the gain and exactly just under 30 dB, which is what we were expecting. So now we have the frequency response of the amplifier, we have its gain, we have its bandwidth, we've already measured this TOI, so we are getting more and more information on the amplifier's performance. And I can go ahead and put a marker, and the marker is going to go to the highest point. So the highest point gain is about 29.2 dB, and I can move the marker forward, and it has nice acceleration built into it, so we can move very slowly, or we can move fairly fast. I like that. There it is. So if you have a gain, let's say at low frequencies of about, let's round it up and say about 29 dB. So the 26 dB, which is 3 dB down, we can go until we hit 26 dB. Right there, we have 1.3 gigahertz of bandwidth from this amplifier, which is exactly what it should be. It's working exactly as anticipated. So now that we have this, we can actually use some of the marker functions and take it to a next level and calculate the noise figure of the amplifier, because we have its gain, we have its frequency response, and therefore we should be able to calculate its noise figure. So let's go ahead and see if we can do that. And then there is some other interesting measurements that I want to do to this amplifier. Okay, let's take a look at advantage of the marker functions. So let's go set up a marker. So the marker is going to be sitting at around 517 megahertz. By the way, that's from my wireless microphone that gets picked up a little bit by the instrument here and by the cables that are coming out. Of course, it's not directly internally coupled. So let's go ahead and under the marker functions, and we can change the marker mode, and we have a few things we can do. We can do noise, frequency count, and NDB down calculations directly on the marker itself. So let's go under noise. And now the marker is going to give us a measurement in dBm per hertz. So at the same time, let's average this trace a little bit. So let's go under trace, and let's go under trace mode and change it to average. And let's enter 16 average points, let's say. So it's going to begin to average that, and I'm going to go back on the marker. I'm going to move the marker somewhere to lower frequencies where we kind of had an idea of what the gain was already, about 28.5, 29 dB of gain. There it is. So now we're measuring minus 100 dBm per hertz. That's the value we're getting at around 177 megahertz. Now, what was the gain of the amplifier? It was about between 28 to 29 dB. So now if we take into account the reference noise of a 50 ohm system, minus 174 dBm per hertz, we add the gain of the amplifier to that. So we have minus 174 plus the gain of, let's say, about 28.5. We get the value of minus 145.5 dBm per hertz. The difference between that number and this measured number up here is the noise figure of this amplifier. And the noise figure of the amplifier is about 15 to 16 dB, which is exactly what we measure using the instrument. So we can, of course, now that we know the gain and we know the noise at the marker, and we know the noise is above, well above the noise of the instrument itself, we're going to easily be able to do this measurement, which is fantastic. So now we know the compression, third order intercept point, bandwidth, gain, frequency response, and noise figure of the instrument, all measured directly using this. So what is missing? Well, we haven't looked at the manual gain control port of the amplifier at all. Now this is where the measurements get a little bit more complicated. I don't want to just measure what the gain control range is. I want to measure what is the bandwidth of the gain control port of this amplifier. So how do we measure that? That sounds pretty complicated. So what if we modulate the gain control with an external source and then measure the demodulation directly on the instrument itself in AM demodulation mode? If I were to modulate the gain control of the amplifier, I'm going to change the output amplitude. So it's going to look like AM modulation. Now this can do direct AM demodulation depth measurement. So we can use that measurement and calculate the frequency response of the gain control port. That's pretty exciting. Let's go and set that up and see what happens. And here is our setup for characterizing the gain control port. So I've connected the gain control port directly to a synthesizer here. This is an adjuvant function generator and allows me to apply a arbitrary function directly to the gain control port. Now remember that a function applied to the gain control mode would translate to amplitude modulation at the output of the amplifier. And the amplifier is of course still connected to our spectrum analyzer here, and the power supply is all the way up here. So right now I'm applying a 1 kilohertz sinusoid waveform directly to the gain control port. Now we can go back to the instrument and see what consequences that has. So we can use the demodulation capability to listen to the AM modulation first, and then when you listen to it, that tone will of course have to match 1 kilohertz, and we can change that to make sure we're hearing the right tone. Once we verify that we can get AM modulation, then we can use the AM demodulation capability and get detailed response from the amplifier. So let's do it one step at a time. Okay, let's configure this. Now I want to do this measurement at 1 gigahertz, so that should be fairly easy. Once again, changing the amplitude. Let's make sure we have a good reference of about 10 dBm. Now we go under measurement here and our source. We're going to set it to coupled CW. So now it's going to be at the center frequency of the span, and there it is. We can see exactly 1.5 gig here. So now we want to do it at 1 gigahertz. So we go center frequency 1 gigahertz. Now let's reduce the span because we don't need to look at a very large span. We can look at, let's say, 20 megahertz. We can go ahead and change the resolution bandwidth, bring that down to something very small. 3 kilohertz would be fine, maybe a little bit larger. 10 kilohertz, there it is. So here's our tone. Now right now I have not turned on the function generator, so there's nothing being applied to the gain control port. Therefore there is no AM modulation, and we can verify that. I can go under marker. The marker is going to take the peak value, which is good, and then we're going to go ahead and go under marker demodulation, and there it is. The marker demodulation can do AM, FM, both directly on where the marker is placed. So now we want to do AM, of course, and let's change the time to 1 second. So it does 1 second at a time. Now if you listen, it's quiet. That's because there is no modulation, but I can go ahead and turn on the modulation on that port, and we should hear a 1 kilohertz tone if everything is working correctly. So let's try that. Here we go. I'm about to turn it on, and there it is. You can hear very clearly the 1 kilohertz tone. Now I can change the frequency of the modulation. That's 1.9. I can go down, let's say 600 hertz. There you go. So you can play with this until you give yourself tinnitus, but I don't want to put you through this. So we're going to turn the modulation off here, and the sound will stop. So it works. We know we can do AM modulation, and the instrument can demodulate that without any problems. Now we can switch to a more advanced modulation analysis, which is built into the unit itself, and I can change the mode of operation of the unit. So let's go under mode, and we can go under analog demod. Now, unfortunately, as soon as I do that, the instrument turns off the source, and there is no way to turn it on. So in this mode, the source is disabled, which is unfortunate because I think it is very useful to be able to do this measurement with the source active. I could not find a way to use the internal source and generate a tone, which means that at this point we have to switch to an external source and apply a 1 gigahertz tone from my synthesizer from the outside. I think if they change the firmware and allow that, if it is possible, which I don't see why it wouldn't be, then you would have so much more ability because you can use the internal source for this measurement. So let's switch to the external source and continue our measurement. So before we turn the tone on, we can take a look at some of these numbers. Now, of course, these are all gibberish at the moment because there is no tone, and the carrier power is detected as minus 58 dBm. There's just the noise of the instrument itself, and all the other numbers are jumping all over the place. We can go in the tone on now. There it is, and as soon as I do that, the instrument detects the carrier power is 6.2 dBm. So now we do have a tone at 1 gigahertz, so everything is fine. Now the modulation index and RMS value, they're all at 0 because I haven't turned on the adjuvant function generator yet. Therefore, there is no AM modulation yet. The carrier frequency offset of about 80 Hz is normal. That's the difference between the crystal of this instrument up converted to 1 GHz and the crystal of the EXG, or the YIG oscillator of the EXG up converted to 1 GHz as well. So that makes sense. There's some frequency offset to be expected. So because there is no modulation, the modulation frequency and so on is also jumping all over the place. Now is our chance to go ahead and turn on the adjuvant function generator and introduce some modulation on purpose. Now I have the function generator set to a 10 kilohertz sinusoid. So let's enable it. And there it is. Now as soon as I enable that, now we're going to begin to see some modulation depth. And we see the modulation frequency is 10 kilohertz. But if you look closely, the THD is minus 8.8 dB, and the signal to noise and distortion ratio is 8.0 dB. That's pretty bad. So why is that? Well, we do have a modulation trace we can look at, and this gives us the AM demodulated signal, which is very helpful because we can see exactly what is being demodulated. So let's go ahead and take a look at it. And as soon as we look at that, we see, yes, we do have these sinusoids. The top of the sinusoids are all capped off. So why is that? Well, that means that the gain control port of the amplifier doesn't react when the signal is very small. So we have to adjust the level of the gain control voltage being applied to the amplifier to create a nice sinusoidal signal. I can do that. I can adjust the level. So instead of the signal going down to 0, let's change the signal such that it goes all the way to 250 millivolt at the bottom level. So there it is. Now we have a nice sinusoid. It means that the frequency coming from the function generator produces a nice sinusoidal AM modulation. Now that the waveform looks much nicer, if you go to the modulation summary, we can see that we have a much better THD, much better signal to noise and distortion ratio, and our RMS value of our modulation is 28%, and the modulation frequency is 10 kilohertz. So how do I measure exactly the bandwidth of the gain control port? Well, I do have the RMS value. I can continue to increase the modulation frequency until the RMS value drops by the square root of 2, and that will be the 3 dB bandwidth of the gain control port. So let's go to the modulation trace, and these numbers are written up here as well. So there it is. The RMS value is 20.7. So I'm going to continue to increase the modulation frequency coming from the adjuvant synthesizer until I hit the value of 14%, which is 20% divided by the square root of 2. So let's go ahead and do that. Should be easy. So now we're right now at 10 kilohertz. Let's go to 20 kilohertz. There you go, 20 kilohertz. We've already dropped. You can see we're already at 18.4%. Nice. Keep going. 30%. Now 16.5. 40 kilohertz. 14.8%. Oh, we're getting there. Let me go to 45 kilohertz. There we go. Perfect. At 45 kilohertz, there it is. Modulation frequency 45 kilohertz. We have an RMS value of 14%. We started from 20, and that's our 3 dB bandwidth. So by using an external function generator on the gain control port and using the internal capability of the FPC1500 to do AM demodulation on demand and get all the modulation parameters, we can calculate and measure directly the 3 dB response of the gain control port of the amplifier. Now this is a fairly complicated measurement if you wanted to do it, but we can easily do this with this instrument because we have every functionality built into it. The only thing missing is I wish the internal source could be used to do this, so I wouldn't have to use an external synthesizer. Then I could just directly connect the generator to the amplifier and do the same measurement, and I hope they add that. So if I go back all the way to 10 kilohertz, you can see that I will get back to where I was. And if I go beyond the 3 dB frequency, so let's go here 70 kilohertz, you can see the AM modulation depth continues to shrink. Now we are at 120 kilohertz, and the RMS value is only 6.8%. So it makes perfect sense, a fairly complex measurement being performed successfully with this instrument. Now let's do a couple of other smaller experiments just to show you some of the other features built into the unit before we use the web interface. So the instrument also has a fairly powerful digital demodulation capability. So we looked at the analog demod. Now under digital demod, if you go under the settings, you can do ASK or FSK type of modulation, but you can fully define the modulation parameters for these two things. There are a couple of standards also built into it, and that includes Bluetooth low energy and tire pressure sensors, which have a well-defined modulation scheme, so it already has that built in. And I hope that they would add more, as some of the most common type of demodulation can be done directly on the instrument. It would make it very powerful, especially for an entry-level product like this one. So, but of course we can generate our own modulation in any way we want. So I have defined an FSK modulation using my EXG vector signal generator, and I can enter all of my modulation parameters. For example, I can define the filter type, symbol rate, frequency deviation, the alpha for the filter. All of these things can be fully defined here. And going back here, we can also change to look at either modulation error, modulation deviation, symbols, or eye diagram. So let's go ahead and enable the modulation. So currently I have a 2-level FSK with the frequency deviation of 10 kilohertz and a baud rate of 100 kilosamples per second. So right now it's disabled, so of course we see nothing. So I'm going to go and enable it. And as soon as I enable it, we can clearly see the FM deviation, and we can see our ones and zeros carrying through, which is great. And this is a very good vector signal generator, so we don't really have any modulation error. So if I go under modulation error, we can see that there is nothing there. Now, more interestingly is, of course, the eye diagram. You can see the eye diagram of the data after it is demodulated. This is a powerful tool to let us know the quality of the signal coming through, and we can also see the symbols coming. Now, the symbols in this case are randomly generated, and I am looking up to 256 symbols, so you can capture a series of symbols and then analyze them for doing whatever analysis that's required. If you're reverse engineering something or there is a burst of errors you want to find out, it also has burst mode processing. So all of that looks good. Now if I go under eye diagram, this is a 2-level FSK. I can configure my instrument to do a 4-level FSK. In that case, we would see a PAM4 demodulated signal. Let me go ahead and change that. So instead of 2 levels, let's go ahead and have a 4-level mode. There it is. Now the eye diagram doesn't look as nice anymore. The SNR of this eye diagram is going to be worse because, of course, it's a PAM4 signal, much more sensitive to vertical eye opening and horizontal eye opening, just because of the fact that it is a PAM4 signal. So there it is. You can see very nice demodulation capability built into it. There's a ton you can do with this. I can spend an hour just talking about different kinds of modulation that we can do and different experiments. But I hope it gives you at least a quick idea of what can be done with this digital demodulation built in. Now, in terms of modes, what we haven't covered yet is the vector network analyzer. Now, even though we looked at S21 measurement, that was a scalar measurement, but this can do a vector measurement on one port, on S11. So we can go ahead and do that as well. And for that, I thought maybe we can do a remote interface. And by the way, this whole time, I had the Wi-Fi of this unit enabled, and it didn't interfere with any of our measurements, which is great. So we can use the computer to connect to it and do our calibration as well as analysis of the input return loss of our amplifier. So we've characterized the amplifier in every possible way. By the way, this FSK signal is going through the amplifier right now, so we can do FM modulation, of course. And now I'm going to see what is the input return loss of this amplifier when it is running, so we can do a vector measurement on S11. So for this last portion, I thought I would use the mobile app from Rohde Schwarz that allows me to directly connect to the instrument through Wi-Fi, and this is exactly what I've done here. And this screen can be configured to show you either file transfer there on the left or remote control of the instrument. Now, unfortunately, in this app, I cannot find a way to maximize the main window. This side panel bar always seems to be there in the view, which is unfortunate. I couldn't find it. Maybe there's a way to maximize it, but it's certainly not very clear to me. But having said that, this is of course really easy to use. Connecting it was instant. There was nothing to really configure. Just connect to the Wi-Fi and type in the IP address, which is what we have here. Now I've already gone ahead and done a full 1-port calibration, and this is really straightforward. You can see that you can do a full 1-port calibration, and if you have a calibration kit, you can define it there at the bottom, and then you can do a regular calibration as you would do with any network analyzer. Now I'm not going to go through that in the interest of time. I've already performed that. But now that I've done that, I have a S11 measurement of the input of my amplifier. And you can clearly see that we have a good return loss starting from about minus 20 dB, and it goes down to minus 35. And then it, of course, degrades to about the higher frequencies. Here we're looking at the full range from DC to 3 gigahertz. So there's a wide range of frequency well above the frequency operation of the amplifier itself. Now I can change the format of this, which is quite nice because we do have a vector measurement, so we can see the phase, of course. And the phase of the signal is going to look somewhat normal at lower frequencies, and then we're going to have a much wider range of change at the higher frequencies. Now, because we do have full phase measurement, we can calculate things like electrical length. We can calculate the failure of a cable at a particular point. Everything that you can do with a vector measurement, you can do here on this instrument. And furthermore, we can look at the Smith chart. So if I go on the format, I can change the format here and look at the Smith chart. and you will see that at low frequencies we are close to the 50 ohm line, and then as we go further away it's going to deviate from the center point of the Smith chart. Now the slowness of this interface has to do with my Wi-Fi network not working very well. The instrument is working very fast. It's not an issue of the unit itself. As you can see, close to at the starting point we're right at 50 ohm, and we go right over the 50 ohm point. That's when there's a dip in the response, and then of course we deviate away, inductive and capacitive and so on. So you can see it's really easy, straightforward measurement. Now if I go ahead and turn off the power to the amplifier, the response of the amplifier will change and the input return loss will actually change. Now the change is not very much, but it is enough to notice. So I'm turning the amplifier off, and there you go. You can see that the return loss at lower frequencies actually improves, and we don't have the capacitive input, the reactive input of the amplifier anymore, and we're just seeing the 50 ohm termination. So it looks quite nice. And if I go back over here, I can change the format back to return loss, and we can see that at lower frequencies, of course, the return loss is going to look better. Now if my Wi-Fi would work a little bit faster, it would be quite convenient, but of course it's going to take now forever to bring us back to the regular display. There it is. So you can see that the lower frequency we are sitting at about -27 dB, and then dropping to below -50, which is essentially an ideal match. So there you go. As you can see, works quite nicely. We've seen the web interface of a variety of Rohde Schwarz instruments so far. They are the best, I would say. It's really easy to work with. They're fast, responsive, and they just work. I also wanted to quickly show you the spectrogram feature of this instrument. Now the spectrogram relies on the waveform update rate. The waveform update rate of this instrument isn't the fastest I've seen, and it's primarily because how long it seems to take for the waveform to be updated after a sweep is completed. So the sweep itself is quite fast, 56 milliseconds, but it does take a long time to generate the next waveform and so on. But nonetheless, if you have something that varies with time and you want to capture it in a spectrogram, this instrument can do that, and you can also play it back. So here's a waveform at 2 gigahertz center frequency. I'm going to turn on some FM modulation on top of it. So clearly the center frequency is changing back and forth, and we can see that. So let's go under measure and let's enable the spectrogram. Here it is. And as soon as we do that, it's going to create a waterfall view, which is color graded depending on the intensity of the signal. And we can see that building up, and the individual highlighted points are the warm points, essentially, is where their peak is moving around. So what I can do is I can go under bandwidth and increase the bandwidth a little bit so that we can get a better view across time. There it is. So now the spectrogram looks a little bit easier to see through the camera. So by looking at this, we can clearly see that the FM modulation appears to be a ramp. So we have a ramp which is moving the center frequency around, and we can see it here very clearly on the spectrogram. So now once we capture some of that, we can go under measurement and we can go under playback mode. And as soon as we're in playback mode, we get 2 time markers, and we can move these time markers. Here's the first one, and as I move it around, I can see all the captured waveforms, so I can catch various events. For example, I can bring it all the way here where the beginning of the waveform is, and I can go to the other one and I can move that to the end of the waveform, for example right here, and by switching back and forth I can see exactly how much my waveform is moving. So this is a very handy tool. Of course, is built into the unit, and this allows you to catch events across time. If you let this thing run for a very long time and you come back and you look for a hotspot and then you bring the marker down to see exactly what happened at that point. It's a nice feature, and I'm glad that it's included. And there you have it. I hope you enjoyed this extensive review of the Rohde Schwarz FPC1500. Now, this was a long video, a lot of effort went into it, so let me know what you think about it. And of course, you can always support the channel through the Patreon page. All the funds coming to the Patreon goes to purchasing new equipment for repairs and tutorials. I'm actually filming several episodes in parallel. There are a lot of repairs and tutorials coming up, which I'm sure you would enjoy. I'm just waiting for some components to arrive so I can finish those videos. You can also always let the vendors know that you enjoy the videos, that influence your purchasing decisions. I don't get any proceedings from the sale of any of the equipment. This is just so that I can have a good relationship with the vendors, and I hope that you find the tutorials also beneficial. Some really cool experiments and interesting videos are coming up in the future, so subscribe and hopefully it'll be released soon.